Okay, so I'll get underway. So this is my version of some insights I think that people in general, depends what discipline you're on, whether it's law, or economics, or management, or project management. I think there's something that we can get out of complexity science. You see, we've been, and I'll get on to some of the authors in a second, we've been duped, really, into what's going on here. And that is, we see the world as well as we're built through our senses, not necessarily as the world is. And if you go back and have a look at some of these authors, I'll just mention them by name, and again you can sort of, I can give you a list of some of these people. These aren't people I'm going to directly relate to, but if you go back to the 1700s, people like David Hume, they were talking about the difference between the world as we see it, and the world as it is. There's a difference. We interpret the world in a particular way through our senses. And therefore that gives us a bit of a problem. One of the things is cause. So the idea about cause. You've got to remember that the idea cause is an idea. It's an idea that we have about the world. We say A causes B, but that's something that we do, that we say. It's not something that exists necessarily out there in the real world. Like having a point, for instance. People say, what's the point of this? Well, having a point is a thing that brains do. It's not necessarily something that the natural world does. Like colour. The natural world doesn't have colour. Colour is something that brains do. It's something that our eyes do. It gives us this phenomenon of colour. So, people were considering trying to deal with the real world a long time ago. You can go back even further back to people like Plato and Aristotle and so on. Wealth of Nations here, Adam Smith, he was talking about how work divides up, how work, the subdivision of work, how prices, there's this long piece in his book about how price are all coupled together. You grab hold of one price, and as you grab hold of it, it's like a knot in a net. It pulls along all the other prices with it. Had he had complexity science, these people here would have been able to, I think, really explain what was, or try to explain what was going on back then. Now when I say they had, if only they had complexity science, what I mean by that is we've got computing power. And that's what we've had since the sort of 50s and 60s, the ability to crunch large numbers and see patterns. People like, this one is Hegel. Hegel, if anybody does phenomenological sort of methods in their research, is the father of phenomenology. He talked about things he called the dialectic. You have an idea, you have an opposite of an idea, and when those two opposites, you have labour and you have conservatism or liberalism, and you have them out there in the world and they fight against each other, and you get this synthesis, you get this combination, so you don't get something that settles, you don't get an equilibrium, you get this constant drive. People like Marx used the idea. I mean, he looked at economics and sort of talked about the economic system and how that is constantly driving itself forward all the time. There's this complexity that's going on there. What I'm going to be using is stuff taken from these people. So James Gleick and James Sorowski, these two people here, Wisdom of the Crowds and Chaos, they're really good, they're journalists, and they've looked at the topic from a journalist point of view to try and see, is there news in complexity science? What's new about this? I'm going to be taking some stuff from Edward Lorenz's Chaos. This is again going back to the sort of stuff in the 50s and 60s, the butterfly effect. Benoit Mandelbrot and Fractals. Steve Wolfram, and how very small patterns, small rules can generate enormous patterns. Even to the point that you can have some sort of small molecular structures that produce something like me and you, of course. Dawkins and sort of an overview of evolution. Barabasi and the idea of networks. So this is how networks work. another brilliant book by Martin Nowak called The Super Cooperators. Super Cooperators looking at how altruistic behaviour manifests. And what you get from that is you get that, you know, we have this idea of cooperation, but really cooperation is a way to compete. Cooperation is a mechanism to use to compete on a group basis. Wisdom of the crowds I've mentioned here, and this one here, a bad little picture of it, is Robert Sapolsky. Also, Robert Sapolsky is a neurobiologist, and what I've done is I've sort of taken some ideas from all of these and I put them together in this map. Let me show you this. So this is a short little presentation here. Now what I'm going to get to by the end of this talk is I want you to have this as a perception of work. This is how work is. If you were to view work, what you do in a project, in an organisation, this is work subdividing, and it looks like it's growing, like a real growing, organic thing. Well, it is. Okay? So what I'm going to do is I'm going to overview some of the structures that go beneath this to show us how this happens and how we can identify this in a cultural environment like an organisation. All right. So two ways of looking. This set of glasses I'm going to look through. One is about clock thinking. The other one's about cloud thinking. We are predominantly thinking like clock thinking. And what I'm going to show you is to try and think like cloud thinking. Okay, this is my little metaphor that I'm going to use for this. So a little bit about clock thinking first. So one of the things we do, now this comes down to us. Okay, this is how we're built. This is a lot of our thinking, so the ways that we think about the world come from the way that we're built. Okay. So our senses and how we get information, and we see things very much in terms of cause and effect. So if you look now in the literature, in any books to do with management, let's say, there's often papers on success factors, the top 10 reasons why. Now, you realize the more you look at complexity science that there aren't any top 10 reasons. It's a lot more complicated than that. But we like to sort of think that if you've got these a few little factors, then that's going to lead in some way or cause success. Also, we look at the world very much in a reductive way of thinking, that it's an additive way. 1 + 1 = 2 and so on. And we get this, you know, there's an Aristotle's idea of all the different component parts that we have. We're machines, okay? And René Descartes and so on took this idea even further. So we've got them to sort of blame for it. We also have this idea of averaging. We like to look at on the average. We look at on the average house prices in our area, whereas really what we want to be looking at is the most frequently sold, you know, house price. So we have this idea about averaging. We have a misunderstanding of this concept of the wisdom of the crowds, that you get enough people that they can guess how many beans there are in a jelly bean jar. We also, when we look at data, biologists are great for doing this, but you know, when we look at data, we see all these outliers, and we consider them to be some flaws, perhaps, or anomalies in the measurement, whereas actually complexity science sees them as real parts of the system. They're ways that the system behaves. And we often remove them, but we should keep them in. It's they, in fact, will tell us a lot about it. Platonic thinking. We have this idea that there is this ideal form. We have the essential rabbit. You ask a child to draw a rabbit, and they draw the ears and the funny bunny rabbit tail and so forth. So we get this Plato's idea of the essential rabbit, the essential chair, the essential triangle. In some sort of sense, from his point of view, all triangles, no matter what you draw, where you see them, are mere imperfections of the perfect triangle. Aristotle saw it differently. He saw that if you looked across, let's say, rabbits or chairs, you look at lots of different chairs, you will see chairness in them. This is where we get the idea of a chair, right? But it doesn't actually exist in any way like Plato decided it. But nevertheless, we get this ideal, there's this ideal, and we see it now. We open a project management book or we open a management book, and we see these ideal forms of how a risk system should be, how a change management process should be. If you actually built one of those, they wouldn't work. We have the ideal project manager. We get these at conferences where somebody sort of stands up and this, they've got this, they're somehow living up to some sort of ideal. And also we have surrounded ourselves by linear systems. We're not really very good at understanding non-linear systems, because the systems we see around us are linear systems, like the amplifiers that we have. Your shower system, for instance, you step in the shower and you turn it on, you get a little bit hot, and then you move it again, it gets a little bit hotter, and so forth. You wouldn't want a non-linear system. You wouldn't want to just move it a little bit and all of a sudden you're scalded. Right? So we surround ourselves with these linear systems. We have rules, a simple rules, 1 plus another 1 plus another 1 gives us a simple sort of counter. Whereas in complex systems, what happens is the systems get to a certain state and then a new rule is created. It wasn't there before. It manifests, it emerges. So, clock thinking, what I was trying to get around in that little concept there is we are polluted with this idea of how the world is. We're surrounded by linear systems. We have this Platonic way of thinking about ideal forms. But when you look at complexity science, it's not like clocks, it's not like cogs, it's more like clouds. They're really hard to grasp. Alright, so I'm going to go through a couple of these little topics here. And that's what you'll get on that little table that I've given you. That's the sort of left-hand side bit. And on there, what I've done is put a sort of what I think is a basic message from each one of those topics. And then perhaps I've had a bit of a think about how they might impact an individual in a management situation. So, let me have a go at this one first. So, chaotic behaviour. When Lorenz was back in the sort of 50s and 60s trying to look at forecasting weather, they had a problem. And the problem is that the weather sort of seemed to behave in patterns, but they weren't repeatable. They were sort of slightly repeatable. And it was really annoying. I mean, that's really annoying. I mean, you'd like a nice, orderly system to be able to use to predict. But he realized that eventually what he came to realize, using, again, computer systems to model it, that all these tiny little winds, these tiny little currents, they are all part of this system. In fact, if you want to know what this system is doing, you need to know what everything else is doing on the planet. All these small little currents all add up. All these initial conditions, all these small changes all add up to have an impact on the larger system. And he found that when you then started to factor those in, and this is the idea of the butterfly effect, the idea that a small butterfly moves here, disturbs the wind. Well, if you have enough small disturbances, they actually mean something, and they contribute to the larger system. Also, with chaotic behaviour, we need to look at things like non-linear behaviour. So, let me just show you this little pendulum. There's a simple little pendulum here that swings. Oops, I need to just rewind that one. So, we've got a simple little pendulum. It swings back and forth. Now, if we break the pendulum in half, we go from something which is very, it's actually a non-linear system because it speeds up and slows down, but now we get chaos into it. Now where the end of that pendulum goes is completely unpredictable. You can model it, you can produce a computer model that does it, but you can't predict where that real one's going to go. Now, the interesting thing is you start to see this non-linear behaviour at different times. So I'm going to get this little system here. These are two of them, right? These are two pendulums swinging together. And you see they'll match each other quite nicely with a slow amount of energy in them. But now, if you could increase the energy in the system, within fractions of a second, they all go out of kilter completely. So again, small initial conditions, small changes in weight, position, speed and so forth will make an enormous effect. Again, you can't predict where it's going to go. So now we're talking about complexity, okay? It's hard to predict, if not impossible to predict. The best way you can predict it is by running the actual model. You just run the system and see what it does. Okay. Another thing that is interesting here is, what I want to try and show you now is give you the background to the idea about this, the ideal. Remember I said there's no ideal. The ideal is a false idea. This is called the Lorentz water wheel. Now it's a simple little device. It's just this is a bike wheel basically with some cups on it, with some holes in the bottom. Now what they've got is they've got a jet of water that's coming into it, and as these cups fill up, they drain slowly, and the water wheel spins back and forth, back and forth. But the interesting thing is that the more water you push into the system now, if you start increasing the energy into the system, you find that the cups don't drain very well. And all of a sudden one side of the wheel gets too heavy, and then it falls back. So you get, it adjusts itself constantly, back and forth, back and forth, back and forth. And if you put enough energy in the system, you get completely chaotic behaviour. You know, when you're boiling an egg next and you look at the pan, if you could see the water in the pan, it actually goes through these these vortex in the water, right? So the hot water is rising all the time until the point gets to it that it just breaks down completely and it bubbles. Now, what we used to do is sort of say, well, that's the system breaking down. Well, no, it's not. That's the system behaving with a high amount of energy in it. So, let me just show you this a little. So if I were to do this, if I was to sort of plot the speed, the acceleration and the direction of that wheel. So imagine this is like a three-dimensional axis here. It would give me a sort of a dot for a particular amount of water that's going in. Okay? Now, if I went and stuck my finger on that wheel, it would slow the wheel down. Oh, and you'd sort of see it move. You'd see the dot change. But if I took my finger back off again, the water would continue running and the wheel would get back up to speed and continue doing what it was doing previously. However, if you start pumping the water in, high energy, you get this sort of behaviour. This is called the regular attractor. It's a point of equilibrium where the system settles nicely. But then when you drive the system hard, you get this. And this is one of the reasons it's called the butterfly effect. See the butterfly wings in here? It spins different directions back and forth. It actually never repeats any of its cycles ever. But the interesting thing is it bounces around it looks like it will settle there. But if you stuck your finger on it and then took your finger off again, it would just go back to this chaotic. It never settles, but it looks as though it does. See, here's the universal. If you looked at lots of chairs, here's the chairness. It looks like it would settle there. If you were to look at different organisations and how they were behaving, they would be all around here somewhere. And it would look as though they should be, there's an ideal. But the ideal is an illusion. It's not real. Okay. And what we get out of this is if you were to sort of say, oh, well, perhaps it does repeat. No, it doesn't, because the more you keep zooming down in here into this sort of system, the more you realise that they're never precisely the same. The wheel never repeats the same pattern, ever. It's never the same velocity or never the same acceleration, never the same direction at the same time. Okay, so that leads me into this idea of fractals, because you can start zooming down into these things and seeing much more detail. Now, we see the world in a Cartesian way, 2 dimensions, 3 dimensions. Well, complexity science doesn't see it like that. It sees it in fractions of those. So, if anybody's seen this little set, it's called the Mandelbrot set. You can have a look at these on the net. But this particular pattern here is, again, this stuff comes about from a very, very simple formula. I'll show you the formula in a second that creates this. But if you keep zooming down, and you keep zooming down, and you keep zooming down, you start to see the same pattern you started off with in the beginning. And if you started to zoom down there, you'd see, and if you zoom down there, you'd see, and so on. You can't get away from it. In fact, it doesn't matter what scale you look at this, you can't tell where you're at. You can't tell whether you're zoomed out or you're in. It all looks the same. There are features, here we go, there are features right down at the small level, which are also the same at the large level. Now, there's the formula that generates it. This is how simple it is. But you can only generate this stuff when you've got computing power. Right? When you can do millions of calculations and generate these patterns. So basically it's something that's being fed back in on itself all the time, an iterative loop. So some simple little ones. You've probably got a fractal thing in your pocket right now, many people. I'll show you in a second. So here's a very simple little fractal, and I'll build that. So, simple rule. Every time you get a line, you keep splitting the line in half. Can you imagine now how small the dots would be here? Right? Now what you have is a fractal dimension to this, and that is, it's in between a dot and a line. It's a line of dots. It's dots that behave like a line. Right? What's this one? So here's another little one. If you watch Toy Story and you see all the animations that go on that look, you know, incredibly real on there. Again, they use this sort of model. But the guy that initiated Pixar originally started off with using this particular rule to generate the mountains and the landscapes. You basically draw mountains out of triangles, and then every triangle you make another triangle out of it, and you keep on going. And you get finer and finer and finer detail until eventually it starts looking like real mountains. So we sort of see this. So all we got is a simple little rule. Every time you get a straight line, put a triangle on it, put a triangle on it, and you get these sort of shapes. Now, what we've got is we've got a finite area in here, but the line is infinitely long, because every time you keep zooming down on the line, it gets longer. Every time you zoom down on there, you'll start to see more triangles and more points. And you keep on going and you keep on going. And we see this in these simple little structures here. There's a snowflake. And the snowflake is constructed in exactly the same way. It's crystal built on crystal built on crystal. The overall crystal that you get is emergent out of the original patterns in the crystal. Okay, so here's another one. You take squares and you start to put these little cubes, and you produce this, the sponge. This is how nature solves the problem of getting blood to within one cell of in your body. It basically keeps bifurcating, splitting your circulation system all the way down. So your lungs work. You know, you've got small lungs really in there, but they have a massive surface area. And you can do this by this fractal type approach. And we use them as aerials, as antennas, sorry, in mobile phones. So you get this enormous amount of space here. So you've got infinite space, and there's hardly any volume in this at all. Okay, so natural systems do this, and they do this by what's called bifurcating. They split. As the embryo grows, you grow, the arteries and blood supply systems are bifurcating all the time. And you keep on bifurcating until you're right down at very, very small levels. So there's a blood source everywhere, everywhere, yet it takes up less than 5% of your body mass. Okay. So these are branching rules. So again, what you could do is it's the same thing. So you create it. You go along so far, let's say a certain proportion of the length, then you branch. You go along so again, you branch, and you branch, and you keep on branching. And you produce what looks like this artificial tree or this artificial fern. But then, now what you do is you introduce a little bit of error because nature makes mistakes. It doesn't quite branch. There's a little bit of difference in the proportions when it branches. And then you get something like this, which looks like a real fern and looks like a real tree. So again, it's the same bifurcating rules that go on here that produce this. Now, bifurcation happens in work. And had Adam Smith known this stuff, and perhaps when you actually go back and read this thing, perhaps you get the hint that perhaps he did, but wasn't quite clear how to map it out. When he talks about how a nail maker works, so a guy's making nails, and this is in Wealth of Nations in the first part of it. So he's making nails, and what happens, he can make 200 nails a day. He's forging these nails, sharpening them, flattening the ends, and so forth. But then there's pressure from the outside, that is, there's market pressure, because people want more nails. So one of the ways he rises to the challenge is he brings somebody else in. Now, he can make 200 nails, and this other guy can do in the same thing with the same forge, can make another 200 nails. You can make 400 nails. But That's if you're completely duplicating the task. But if we now specialize, we bifurcate the work. We split the work, and that is, I do all the stuff with the forge, and you do all the stuff on the anvil. Now I become very good with handling all the forge stuff, and you become going very good with the anvil. Instead of producing 400 nails, we produce nearly 600 nails. This is work bifurcating. Okay? So when you look at, and now what you get then is you get specialization in each one of these. And then work again, given pressure from outside, market forces. Again, the work, if we need to rise to the challenge, that is, if we're going to continue making nails, we could decide not to, and then we just go out of business. Or we could rise to the challenge and we could bring in another person and look again where we can bifurcate the work. And we see this, again, naturally. Here is looking up through a set of trees. Here is a slice of somebody's brain somewhere. Alright, now here's the scary thing. Here is the scary thing about fractals. And so every time you look out of a window, I want you to have a think about this. What I've just said about how the tree leaf is produced, and the shape of what goes on here doesn't necessarily have to be, the structure this doesn't have to be programmed into the genes. It can be a quality of the structure. So, as a piece of wood, let's say, that's growing, gets to a certain size, or plant cells get to a certain size, there's some physical properties about it which cause it to bifurcate. Okay, so it doesn't need to be something that's programmed in genetically to this. But what you see is you see the patterns. You see the pattern in the leaf. You see the same branching, and there's great papers on this. You see the same branching rules that happen inside the leaf that happen in the branch and along to the tree. Now, here's the scary thing. There's some great studies that have looked at the whole forest. And you find that if you've got a forest which is just of the one tree, there is a relationship between the spacing on the trees and the branching in a leaf. Now, if you get so one network here, and then you get another forest or group of trees that come in on top of that, then you get this complex pattern that emerges between them. But to look at what you see out there, if you see the spacing of the trees given time, dropping of seeds and so forth, given time, the pattern that's built up here has its structure which lays right down here at the cellular level. Well, that amazes me every time I think of it. Okay, fractal dimensions. We see fractal dimensions in work. Look at projects for a start. Tasks, projects, programs, portfolios. They all have this start, middle, and end. See if there's a similar structure. We see start, middle, and end to a task, and start, middle, and end to a project, and start, middle, and end to a program, and so forth. And you see there's this sort of fractal behaviour. The interesting thing to get from this then is if you want to try and change the structures of these things, you don't want to go fiddling at the portfolio and the program level. You need to go down to the task level. Because then what emerges out of this, the forest that emerges, or the program that emerges out of this, has the patterns of what's down at the task level. So we, I think, wrongly approach this. We try and go for a top-down approach, but really it should be a bottom-up approach. All right. Wolfram's stuff. Now, I just want to show you this because this again is pretty cool. So, these are cellular automatas. This is a simple little program, right? Because line by line. All you do is you start with a row of white, then a black one, then white. And then you work systematically across here, and you look at this set of rules to decide what this is going to be. So I see whites in front of me, white, 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 white. And then I get to this point and I see a white, and a black. So white, a white, and a black. I'm black, right? So now this one, what do? I see a right, I'm white. So can you see how this rule set produces this? So you go to the next row and then you decide what you are. And the interesting thing about this is, from the rules, you can't tell what the pattern's going to be. You can't tell. The only way you can tell is by running it. By unfolding this, do you see what the pattern is? You can't look at this rule and say, oh yes, I know, it's going to produce this nice symmetrical pattern. So what Wolfram has done hundreds of these. Here's an interesting one here. So this particular rule, now this particular rule 30 is a famous one, because rule 30 turns up in real shells like this. There it is. This manifests because, of course, the shell is growing in the same way. Okay, it's growing layer by layer by layer by layer by layer. But there is a set of rules that are creating the pattern. Now, the interesting thing out of this is this. It's not only that it appears there, but the interesting thing out of this is that, look at this. There's symmetry going on here. There's order, there's structure, and there is also chaos at the same time. This rule here generates order and randomness. Okay, now, I'm going to move on. This set of rules is a bit more complicated. What I'm building up to is how we work, how cells work, right? A very basic form anyway. What this rule does now is, instead of looking at what happened last time, it looks another layer back, and it sort of says, okay, so it was a black cell here, row of these, but what's back here as well? So what was affecting this one also now affects me. And you generate these fantastic patterns. So they're not these sort of triangle things anymore. You get these long chains and these threads, and these chains that wind in on each other. And then these look scarily like, I'm going to beam us along to something else now. They look like DNA. So you can have very simple rules, here's the key, very simple rules. That's all Rule 30R was. It's a very simple rule, but generates an enormous, complex pattern. And we know, if you look at this, this is it. Here's the set of genes, and you keep winding. If you ever have an extension lead in the garden, twist it up, you keep winding it, or an elastic band on a plane, and you keep winding it. After a while, it twists itself, and then all of a sudden it buckles, and it produces another set of coils. And it gets so tight then you can't even get, it won't make any more spirals on that one, it'll buckle somewhere else. So you get this buckling upon buckling upon buckling and twisting, and you get these fantastical shapes. They are just a property of the material. They're a rule embedded in it. Now, this is how you're built. This is how we're built. Right? However, there are also these things. So there's genes, but there are the idea here is that there are also a mimetic quality as well. There are things that not only replicate biological structures, but they replicate cultural structures. So, for example, if you fold an aeroplane, the meme of the aeroplane is the folding instructions. And that gets passed on to every scoutmaster and adult who shows their child how to fly a plane. Okay? Court proceedings, the meme there. There are rules and guidelines that you follow. There's an algorithm that's gone through, that's picked through, that generates this behavior that if you walked into the room, you would say, here we are, this is a court proceeding. You'd know it by looking at it. But the thing that's generating it is this algorithm which gets passed on and gets passed on. It's got passed on down the ages. The rules that we have for meetings, how meetings start. We have an agenda, people who are present, and all that sort of stuff. Right? Those sort of structures there. Rugby games, football games. There's an algorithm there. The person who's got a referee keeps reinforcing that the rule is played all the time. And this gets passed on. Now the interesting thing is this. The next place I'm going to take you is to selection, to the evolutionary idea. Because these get selected. If you select this behavior, so let's look at, I'll pick on the courtroom behavior for a second. We walk in through the door and we see this thing called a courtroom going on. And this, in society, seems to function well. It's getting the results that we want it to get. So what happens is the algorithm that generates it gets to survive. The ones that you go into that don't seem to be functioning well and aren't getting the result that society wants, they don't get selected. They go extinct. So what you end up doing is you end up having these structures, these cultural structures, selected. Here's the key. This is what I want you to get, right, out of this. Normally we would think about it's just this cultural practice that gets selected, but what's getting passed on from person to person is the me. It's the algorithm generating it. Okay? So this is what evolution is about. Evolution is about preserving those rules, those underlying rules that generate this great behaviour. Darwin, I was showing you his book at the beginning, then The Origin of the Species. He starts off, brilliant book, if ever you're looking for a Christmas read, I recommend it to everybody. There's no technical, no formulas in there at all. Starts off romancing the reader with domestic selection. How do you go in 400 years from a cow that looks like that to like that? And you start selecting, basically. You milk them, you find out which produces the best milk, and you breed from them, and you don't breed from the others. And you keep on going until you end up with a cow that has others bigger than itself, almost, right? Same thing with carrots. That's what carrots really look like. This is what carrots look like a few hundred years after we keep selectively breeding them. We ditch the carrots that don't look the right shape, and we keep the ones that do, and we breed from the seeds of those. This is selection. In the same way, court proceedings or meetings or whatever they are, as I said previously, we just keep the overall structure. See, we don't think about the DNA in there. We just look at the shape of it, keep the seeds and put them in the ground again. But what's being passed on is the structure of the DNA. That's what's being passed on. What Darwin did is he looked and he sort of said, this happens in the natural environment too. The natural environment selects this. I mentioned Thomas Malthus's stuff earlier on in the beginning because it was really when Darwin read Thomas Malthus's idea about population selection that the lights went on for him. So here's a good example here of how evolution happens in a natural environment. In the Industrial Revolution, this is called the peppered moth. So basically the moth looks like this originally, and it sits on bark that looks like that. So you can't really see it, right? But then what happens is the Industrial Revolution comes along, and it puts soot everywhere. And it covers all the trees, and the bark of trees in the north of England, with black soot. Now, as these butterflies are mating and producing offspring, some of the offspring that are produced have more black in them than white. And what happens is the ones that sit on the black trees get picked off less. So you go off now in a tendency towards blackness. So as moths are born, the moths that are produced, the ones that are blackest, have a better chance of surviving, and then they've passed the blackness gene on. So you end up in a few years with none of those left, and they're all black because they've matched into the trees. So what I want to try and get here is that there is no point to the evolutionary algorithm. Having a point, as I mentioned earlier on, is something that brains do. This is pretty much arbitrary. I mean, the Industrial Revolution came along and now it's changed the colour of the moths. Right? You know, it just flips. They're sort of vectors, but they just flip and flop back and forth. So there's no, like, going back to Aristotle's idea or Plato's idea, you know, that there's some sort of ultimate destination. You've all seen that picture of Aristotle's idea of the evolution of man, you know, and it goes 8 monkeys, something, and there's a man crouched in front of a computer. But there is no direction, really. So we get camouflage and mimicry, and things tend to look. Now this is how these creatures become shaped by their environment, and this is what I want to get over here in this little point, is that the evolutionary process shows how the structures that are in them are shaped by the environment. The role of the manager, the role of the project manager. We didn't just think this thing up. It gets shaped by the environment that it lives in. Okay? The features and the tools that you use, these tools that you end up using, I'll go back to this in a second, the tools that you end up using are shaped by the environment, and there's a large amount of selection that's going on, which is out of your control. I mentioned about the paper airplane there, and I've done this in various sort of forums. You can make a paper airplane like that in a few seconds and fly it, and it goes boom, straight on the floor. But kids are entertained by that. That's great fun. But you can spend 20 minutes on watching a YouTube presentation on making a fantastic plane, that when you fly it in a conference room, it goes right across the top of people, and everybody goes, wow! But I can't remember how to make that thing. I have to watch a video every time I do it, right? And I have to pick 3 or 4 versions of how to do this. But what gets passed on is the simple version. See, it's not performance that gets you selected, necessarily. It's ease. So often when we look at best practice, it's not best practice. It's what's the easiest practice. Another thing I just wanted to draw your attention to while we're looking at this idea of evolution is that evolution happens to a population. It doesn't happen to individuals. It happens to populations. And one of the things I think we need to do is we need to rethink our definition of the individual, because we aren't. We're part of this superorganism, okay, and versions of it. I'll explain a little bit more in a minute. Now, what we see then out of the evolutionary process, and this is another big thought, like the idea of the fractals and the trees and stuff. This is another big thought on this, right? That everything you see here is built in order for the organisms itself to be able to capture scarce resources. When you look at a tree, if you look at a tree out in the park out there, a tree, and you see this fantastic trunk on it and the branches, that tree is not in its natural environment. Its natural environment is over there, and it's fighting for sunlight. And the trunk is a structure that is born out of the fact that if you're higher than the other structures around you, you get to capture more of the scarce resources. So a trunk is a tool. It's a device used to elevate you to the point that you can capture more scarce resources. Now, once you grasp that point, then you can take that to everything. So if you're an animal that munches on grass, because that's how you eat, and that's how you don't eat other animals, you graze on grass. If you're going to compete for scarce resources or compete for a mate, then you end up growing weapons. Because that's how you haven't got the teeth to bite something, only they're only good for biting the grass. But if you're an animal that does eat other animals, you've already got weapons to use. So one of the things you end up evolving is a set of shields. And then we get this fantastical mane around, this is, something wants to bite you around the neck, a fantastic chunk of hair is a really good shield. So we get these structures, that whole structure there, that whole structure in the tree, the whole structure in these animals here are formed out of competition for scarce resources over large periods of time. And we get this co-evolution. The reason that this gazelle here is so fast is because all the ones that are slower than it get eaten, and the fast ones get to breed. Same thing with the cheetah and so forth. So we get this co-evolution that goes on. Now when predators are low, when you're not getting eaten by stuff, there's another thing that you need to compete for, and that's a mate. And then we get sexual selection comes in. Darwin's second book, The Descent of Man, is really good on this. But the idea then you get these fantastical colours, because what these colours do, or these sounds, is they push physiological buttons for the female. Now the brilliant part about it, now there's a complete aesthetic part of this. It feels good to look at something. So you select it. There's the arbitrary part, again. Humans' tools. Now we got all these things. So we generate all these tools, we make tools that make tools. We make tools that make tools that make devices. We're tool makers, that's what we do. And they become fantastical. We can now sail the ships and fight other people while we're sailing the seas, because we produce this tool. Our ideas about things, not only that, if we have an idea that we live on, that we have an immortal soul, we generate all these fantastic things just based on these simple little ideas. So, small ideas, local rules, generate massive behaviour. Alright. Networks is the next little piece to look at. So with networks, what I want you to get out of this thing is that you see networks everywhere. You know that wheel I showed you at the beginning, Lorenz's wheel? There's a network. All the cups are coupled together. There's a strong coupling between them. If we were to put a much more sort of flexible arm on them, now they'd be loosely coupled. But they're part of a network. They're all the same cup. We are part of a network because we're all humans. Ants and so forth, they're not part of our network because, well, they're ants. But they're all part of an ant network. So there's a clone part. Members of the network are all the same. Okay? So when you get networks working together, you get fantastic behaviour. So this one, this short little thing here, if you were to look at a map and you look at how many roads go in here, you'll find there's a normal distribution. There's a sort of an average of, let's say, 4 roads go into a city. But if you look at a flight path, then there are super connected hubs and there are lesser connected. So there are some airports which have so many flight patterns on them, they're enormous. And there are some way out in the bush that have hardly any. Now what happens is this, is that those hubs, those super connected nodes, they shape how the network moves. Because if you knock out one of those, you cause a problem. If you take out the ones out here, hardly anything happens. So we see these networks, we see flight paths, we see the internet and how people are connected together. We also see a human brain and how the cells are connected together. I mean, they look pretty much the same. Right? You know, there is this pattern that we start to see emerge out of here, that we've got things connected together. So when you're talking about complex systems, you're not talking about the individual components. What you talk about is the relationship between them. How do things connect together? And as soon as you start about connecting, you're talking about networking. So let's go back to Adam Smith's on the nail maker guy, right? So I got one, all of a sudden one making the nail. The next minute we have 2 people making nails. But we're connected through the work. See, there's a network here. The work bifurcated. And now what we've got is 2 points instead of 1 point. But they are connected through the work. And we need, that's a communication channel. You know, I'll be shouting back and forth to the guy at the forge of what I'm doing and so forth. So that's how we're coupled. We see networks here. So again, here's a network. Each bird has a set of rules of how it flies. It matches the trajectory, it has a safe distance from another bird, it avoids stationary objects or what look like a stationary object. I mean, you put tens of thousands of them together, you get this fantastic structure that emerges out of it. And that structure is useful. It's useful. Here goes the evolutionary part, right? The structure is useful because it allows them to catch prey. You would, if you were a hawk or a falcon, you wouldn't want to attack that thing. It looks like a monster. It looks huge. And also, you increase the chances of finding a mate and finding food. So that structure is useful to each individual bird. So the birds, that when they all have the rules that create this structure, gives them a competitive advantage. And that means that birds that create this structure get carried on into the future. Okay? So there's, I suppose, all that. So here we are. This is a slice through a tree. This is a slice through a tree, and these are the cells in a tree. But we don't sort of think of them like this, because they don't move very fast, cells in trees. But they are networked together. They just move a lot slower. If you see one of these sort of speeded up camera versions of trees growing or plants growing, you can see that they have movement. Just time is slowed down. So all that local rules. So what I'm going to try here and just pull on some of that stuff that I did with the cellular automata stuff, that Wolfram's, the rules, right? So now we've got one cell. Here it is. Here's me, right? One cell, so I start. And then I divide. And then as I'm dividing, the structure is dividing. The cells that are around me, here's the rules, remember? Like the black squares and the white squares. Depending on what structures are around me, affects how I develop and determines what sort of cell I become. And then I split. And then there's another mass which has an impact on what I become, and so on, until you keep unfolding it, until you have you, or me. So there are unfolding, that's how it unfolds. So again, if you want to try and place this back in management here, you put policies and processes in place. See how these are a top-down thing? Policies and processes and practices in the business are a top-down thing. But what they're actually doing is they're saying to you, here's a particular way I want you to behave. It's giving you a rule. And you will enact that rule. And so will you, and so will you, and so will you, all in this business. And we'll enact these rules. But it's almost impossible to figure out how that rule is going to play out until you play it out. So another way of looking at policies and practices and procedures is that's what we're doing. We're going down to the individual level, we're tinkering with their rules, and then we stand back and say how it works. Now when we select that overall behaviour and we think, yes, this company's working well, what we've got to remember is it's not necessarily the people that we're taking. We need to take those rules, because it's those rules that generate that overall behaviour. You put one ant on the table, nothing happens. You put 10 ants on the table, nothing happens. You put 20,000 ants on the table and they start solving a food sourcing problem. Now the interesting thing about networks is we are so hung up on trying to get procedures and practices right and perfect and ideal. Whereas these systems aren't ideal at all. They're full of error. Remember that, again, having that rule 30 that I showed you, you get symmetry and error at the same time from the same set of rules. That's what you get here. These ants out here, they're wandering around and people step on them and they just wander off into the grass and die. There's randomness going on here, but at the core, overall, they are sourcing food. So one of the things that we're hooked up on is to try and make these procedures perfect, whereas actually the error in it makes them robust. Again, down to the network, I can take out a whole pile of ants, I can take out a pile of ants here, but there's still enough ants to build the system back up again. Alright, coming to the last couple of screens. Another topic to come out of complexity science is game theory. So, how does this play a part? It plays a part in that when I'm talking about these individual parts of the network, these nodes, these ants, these people, whatever, or these birds, whatever they are, the thing that we focus on in complexity science is not the thing in itself. What we're focusing on is the relationship, how it relates to something else, how it deals with something else. When something comes along, how does it respond? And this is where game theory comes in, because it looks at how the entity responds to the other one. And then it's that accumulation of those responses that generate the overall behavior of the group, the organization, whatever they are. So there's a model for this called the prisoner's dilemma, where you're given, you bring in two people where they're accused of a crime, we can't properly prosecute them because we don't have evidence. What we need is to get them to confess. So we're going to strike a deal with them. And the deal is if they confess, they'll get a really, really light sentence, almost nothing, but the other one will go to jail. But of course they also know that the deal is also, they know, they're not stupid, that the deal is going to be struck with the other criminal as well. So now what's your options? Here's your dilemma. What do? Do you stay silent and hope that the other person stays silent? Or do you defect? Do you say, yep, we did it and it was all his fault or her fault or whatever it was, right? So in this situation, of course, when you ask people to play this game and run this scenario on a one-off basis, the default for this is defect. You dob the other one in, right? However, if you get to play this over and over and over with people, you actually learn that it's actually better off to cooperate. And what I'm trying to get here to you is that we have this idea of that things cooperate out of the goodness of their heart, right? And from complexity science's point of view, remember, cooperating, harmony, is something that our brains think up. What really goes on out there is that there is a strategy that helps you win, helps you compete, if you join forces, if you leverage off something else. So, I do this with some students here. I get them to play a game, and if they put a C on a card or a D on a card and cooperate with the defect, they get, so if they both have C's on their card, they both get $3. If one has a D and one has a C, then the one with the D gets $4, right? But if they both put D's, then they get $2. So if you ask them to play it first off, people write a D because they want $4, right? They don't want 3 or 2, they want 4. D. So of course they both get 2. Damn it. So now you can say, well, okay, we're going to play this for a while now. So after a while, you start to see that they start to learn they try to read what the other person's doing. And eventually it comes to a point where one starts to cooperate and the other one goes, and perhaps inevitably it falls back to this position. Right? But what people do is they try to read other people, and they sort of say, oh, okay, well, he did a cooperate just then. Perhaps he'll do a cooperate again. So I might do a cooperate, and then all of a sudden they get locked in here. And now they start cooperating. And this is really interesting. If you start to tell people that, okay, this is your last go now, where do you think they go? Just that last $4. But if you know that you are developing this relationship and the relationship is ongoing, then working along with them is to benefit. It's still selfish, you see. It's still to benefit to you. Okay? So what we find is this, that it goes through a cycle. And this is what you get out of Noak's book, is that this whole cycle that gets played. We have this idea that eventually we will all end up cooperating, but that's not what happens. What happens is we all cooperate, and then somebody takes advantage, and then it all spirals out of control again. Right? Because you have to take advantage. Taking advantage is growing that extra few inches amongst the other trees. And there are great benefits in that. So what happens is you start off defecting, then you play tit for tat, punishing each other. Then after a while, people try to misread, and they misread what's going on. And you get this generous version of tit for tat, where people try now to read the other one, and they try to think what this other person's thinking. And they think, well, oh, hang on a second, did they say D or C? I can't remember what they said. I think they said C. See, so there's error in the system. And once you introduce error into the system, it helps the system cooperate. So here's a good thing. Here's the thing to get out of this. 100% pure communication is not necessarily a good one. Because sometimes when selfish tendencies come through, people play here. If there's mistakes that come through and they're favourable, you end up producing all cooperate. Now here's another last thing to get out of this that comes out in Noak's book, and that is if you make people's behaviour visible, they cooperate more. The behaviour is more cooperative if they know that their behaviour can be seen. That's how this energy rating system works here. Okay? It would have been a good idea in this country if we'd done it with the carbon tax. Right? So they're taxing everybody, just make it visible what everybody's doing, and then the market ends up selecting. Okay, last little thing then is, I want to finish on this one, which is emergent behaviour. So one of the things I want to try and get through to on this point here is that I talked about small local rules and how they add up and build up and create this fantastic overall behaviour that we view, either in a biological sense, or when we walk into a company and we see a company function, or we see a courtroom system function, or marketing, whatever it is. There are a set of algorithms working at a local level, which when you add them all up, and they all connect together, they produce this behaviour. Some of the things I was going to show you here in the coupling, I'll zoom down into this one and just show you this one quickly. You know, what we've got here is this. You know, this happens in a physical sense. So they've got some little metronomes here, right, and they're all swinging out of tune. So what this guy does is he picks. They're on a board, right, and he picks them up. And as he picks them up, he puts them on the board, and there's some Coke cans here. Now, what's happening is that these metronomes have now become connected to each other. They become connected to them because the movement here gets transferred, because this board is moving now, to the others. And all of a sudden, you watch them. And they all work in synchronization with each other. They'll all connect up. Okay? Because they are coupled together. Previously on the table, they weren't coupled. No energy could move between them. But now they're coupled on this sort of system here. So coupling happens in, it manifests in lots of different ways. A mechanical way like this, or players on a rugby field. They are all coupled together. Again, see the players on a rugby field as a network. You can tell that they're coupled together because you can go out and you can stop the coupling. You can plug their ears and you can blindfold them. What a fantastic max that would make, right? But what you've got is you've got this network that is behaving and responding to another network, and it is coupled, loosely coupled, through sight and through sound. We look at, in the Victorian era, we try and put our ideas on top of things. We call things a queen bee. We call things soldier bees, soldier ants. We have this idea, so we take our social ideas and we put them on top of the natural world. Again, right back to Hume stuff, right at the beginning, how we misinterpret what's going on. But what we find now is that there is no queen bee. I mean, there's a bee that we call the queen, but she's not in charge of anything, right? And in fact, if you were to look at bees, I mean, they have an incredibly complex society. This is a great publication here. And it shows how the whole thing, how the system, depending on how do you choose what job to do if you're a bee? Well, it's got to do with things like your age, and it's got to do with things like the pheromones that are around at the time. And that's got to do with how much honey is coming in. So, as pollen's coming in, and as the pollen is coming in, that regulates the behavior of the bees. Because that triggers something which triggers pheromone release and so forth. And on this goes. Now that structure, those individual rules and those individual bees have again undergone selection, because those behaviors that work well, that cause them to survive, they maintain. The other ones here that don't work so well, don't allow them to compete so well, they die off and go extinct. So you end up with these enormous complex structures which basically function down at the bee level. My last thing here, wisdom of the crowds. Francis Galton, one of the guys I was mentioning at the beginning, went around to these county fairs and looked at guessing at this ox. And I think in the paper, what they had to do is they had to guess not the weight of the ox as it stood, but what it would be when it's sort of cut up and hung up to ready to eat and so forth, how much it would weigh. And all these sort of people were putting the tickets in a box, and eventually, of course, nobody won because nobody actually guessed the right amount. But Galton, who was, I suppose, the father of standard deviation and all that sort of stuff, cousin of Darwin, he collected all these sheets together and did some analysis on them, the standard deviation and a few other things, and then looked at the mean, looked at the average, and found that it was within a small margin of error to the actual weight. The point being, of course, is you had this large amount of guessing that went on. But what's interesting out of this is that you can't just have anybody guessing. You need a particular group of people to guess. So a wisdom of the crowd comes from that network. So the people that are guessing here are farmers, and they weigh stuff like this, right? They know what the weight of this is, and if you get enough of them having a go at it. So one of the things to learn out of this is that when you're sitting in a group of people in a meeting, you're asking people's opinions or insights on things, you've got to be careful who's in that group. Because if you want the wisdom of the crowds to function, you can't just get everybody in, because that pollutes the answer, that pollutes the result. What you need is you need the specialists in that can contribute, and overall they give a large group answer. Here's food for an ant, and here's the ant's nest. Right? I just want to show you how this works in practice. And here's the ant's nest. I mean, this is 1,000,000 miles for an ant, almost, right? So how do they get, and you've watched them, I'm sure, there's plenty of ants in Australia. You know, we watch these ants drag this stuff all the way through and eventually they get it back in there. Well, they do it in a simple way. Every morning, or whenever it is, that the ants leave the nest, they leave a pheromone trail, and it's a finite amount. That means it wears off, right? So the closer you are to the nest, the denser it is, and it's weak when it comes out here. So basically what happens is, a couple of ants grab hold of something, one grabs hold of something, they start tugging it, and of course eventually a few of them start tugging it. It's all selfish behaviour, because they all want the thing, they all want the food. But what's happening is one ant will be able to follow a pheromone trail and find one. And as it finds one, the other ant's pulling it off this one towards another pheromone trail. And can you see that eventually, if you keep pulling along the track towards denser and denser pheromone trails, you end up back at the hole. So again, now if you put a beetle in there and a spider in, it makes no sense. Because they don't contribute to the network. You don't get the wisdom of the crowd's behaviour. Only if you get all of the same ants. So again, you know, when we had these, in management often we have these risk workshops and we're asking people to guess on what the risks are going to be. If you just get everybody in, it's like mixing the spiders and the beetles and everybody else in. Right? You need to be careful about who that population of people are to get wisdom of the crowds. And I think one of the one of the challenges for organisations is to try and harness the power of this wisdom of the crowds. We see it now when, if you're looking for information on things, you go and ask the internet. You just type it into Google. There you go. It's not just randomly looking out there. It's looking at in particular sites that have been hit on by other people previously. And my last sort of slide here is relates to how Robert Sapolsky, one of those books I recommended in the beginning there, how he looks at human behaviour. And this really connects right back, I suppose, with Hume's idea about something causing something. Something happens to me and it causes me to do something. How the idea of cause is a human construct. When you look at Sapolsky's stuff, and as I said, he's a neurobiologist, and the research that backs this up is enormous. When you look at how somebody behaves, what he does is he sort of says, well, let's take a step back here. Let's look at what was going on in that body first before it happened. Then let's have a look at the stimulus that caused this to happen. Then let's have a look at what hormonal things were going on at the time that were triggered just before then. Then let's go back and put it into a cultural context. Then, see, where's the cause? You know, it's lost in this huge complicatedness of lots of stuff happening here that leads up to this point. And then, of course, the interesting thing is that we end up behaving, and a few seconds after we behave, we become aware of what we've done. Right? So, you know, there's this, it really pulls back to, and I mean, we can only do this when we've got number crunching ability to be able to look at these, to be able to look at the patterns of those ants that are generating all this sort of behaviour, to model complex systems, to see patterns. So the keys, I'm going to finish up in a second, so the keys to this is, what I've tried to do on that little table there is plot out on the left-hand side each of those concepts as I've gone around them. Some of the key features which I've tried to drag out, and then perhaps how they might apply, not extensively, because you know you could be here for hours and hours trying to do this, how they might apply in a real-life management sort of setting. That's me done.